Okay, this is problem 3a from section 2.3. We're given two linear transformations. The first one, t, is from p2 of r to p2 of r, defined by t of a polynomial f is equal to the derivative of f times 3 plus x plus twice f of x. The second linear transformation is u from p2 of r to r3, defined by u of the polynomial a plus bx plus cx squared to be equal to the vector a plus b, c, a minus b. Okay, we also let beta and gamma be the standard ordered bases of p2 of r and r3 respectively. The problem is to find these three matrices. The first one is the matrix of the transformation U relative to the bases beta and gamma. The second one is the matrix of T relative to beta and beta. And the third one is the matrix of UT relative to beta and gamma. Okay, so we first work out the first matrix. So first of all, we write down the elements of beta, which is 1, x, and x squared. That's the standard basis of p2 of r. We work out u of each of these, and then we compute the coordinate vector relative to gamma. And these will be the columns of our matrix. Okay, so first of all, u of 1. We use the formula up here where a is equal to 1, b is equal to 0, and c is equal to 0. And that'll give us the vector 1, 0, 1. Okay, and now we want the coordinate vector of this relative to gamma. So in terms of the standard basis for R3, the components will just be 1, 0, 1, but we need to write them vertically. Okay, so next we compute u of x. So now up in the formula here we put a equal to 0, b equal to 1, and c equal to 0, and we obtain the vector 1, 0, minus 1, and the coordinate vector of this relative to gamma will be the vector 1, 0, minus 1. Okay, now our next thing we do is we work out u of x squared. In the formula up here we let a equals 0, b equals 1, and c equals 0, and we obtain the vector 0, 1, 0. And in terms of the standard basis of R3, this is simply the vector 0, 1, 0, and therefore the matrix of U relative to beta and gamma is the matrix 1, 0, 1 in the first column, 1, 0, minus 1 in the second column, and 0, 1, 0 in the third column. Okay. So now the next thing we'll do is compute the matrix of T relative to beta. Okay. The matrix of T relative to beta. So it's understood we have a beta down there and a beta up there. So we write down the elements of beta, which is 1, x, x squared. We work out t of these guys, And then we compute the coordinate vector relative to beta for each one, and these will form the columns of our matrix. Okay, so first of all, we compute T of 1. Okay, so that's going to be the derivative of 1 times 3 plus x, which is 0, plus twice f of x, which will be 2, so that's equal to 2. And now we want the coordinate vector of this. So in terms of the basis 1 x squared, this is 2 times 1 plus 0 times x plus 0 times x squared. So the coordinates are 2, 0, 0. Okay. Next we work out t of x. So it's a derivative of x, which is 1 times 3 plus x plus twice x, and that simplifies to 3 plus 3x. And now the coordinate vector of this, in terms of the standard basis 1 x squared, it'll be 3 times 1 plus 3 times x plus 0 times x squared. Okay, finally, t of x squared will be the derivative of x squared, which is 2x times 3 plus x plus twice x squared, and this will simplify to 6x plus 4x squared, and that means that the coordinate vector of t of x squared relative to beta will be, that should be a 6x. So this is 0 times 1 plus 6 times x plus 4 times x squared. Okay. All right. Okay, so we put these three vectors into our matrix. So the matrix of t relative to beta. Okay, so the first column is 2, 0, 0. Second column is 3, 3, 0. And the last column is 0, 6, 4. Okay, so what's next? Next we will compute the matrix of ut relative to beta and gamma. So again, we write down the elements of beta. That's 1, x, and x squared. This time we work out ut of these. And then the coordinate vector relative to gamma for each one. And these will form the columns of our matrix that we want. Okay, so from before, well, ut of 1 equals u of t of 1, and we already worked out before that t of 1 was equal to 2. Okay, so for u of 2, we go back to our original formula for u and put a equal to 2, b equal to 0, and c equal to 0, and that will give us the vector 2, 0, 2. Okay, and that means in terms of the standard basis of R3, the components will be 2, 0, 2. Okay. All right. So next we work out ut of x, which is u of t of x, which is u of, okay, now before we worked out t of x to be equal to 3 plus 3x. So back in our original formula for u, we put a equal to 3, b equal to 3, and c equal to 0, and that will give us the vector 6, 0, 3 minus 3 is 0 there. And the coordinate vector of this relative to gamma will be 6, 0, 0. Okay, so next we work out ut of x squared, which is u of t of x squared, which is u of, now before we computed t of x squared to be 6x plus 4x squared. 6x plus 4x squared. So back in our original formula for u, we put a equal to 0, b equal to 6, and c equal to 4. And we get a plus b is 6, c is 4, a minus b will be minus 6, and the coordinate vector of this relative to gamma will be the vector 6, 4, negative 6. And now we can write down our matrix. So the matrix of ut relative to beta and gamma will consist of 3 columns. The first column is 2, 0, 2. The second column is 6, 0, 0. The third column is 6, 4, minus 6. Okay. Alright, now in the last part of this theorem we compute the same matrix, but this time we'll use theorem 2.11. So we're going to use theorem 2.11 to verify our result. Okay, so by theorem 2.11, the matrix of ut relative to beta and gamma is a matrix of u times a matrix of t, and t is relative to beta and beta. Okay, now our beta must go down here and our gamma must go up there. We computed this first matrix to be 1, 1, 0, 0, 0, 1, 1, minus 1, 0. And the matrix of t, we computed that to be 2, 3, 0, 0, 3, 6, 0, 0, 4. Okay, so we just multiply these two matrices together. That'll be a 3 by 3 matrix. So in the first entry we'll get 2 plus 0 plus 0 is 2. Then we have 3 plus 3 is 6. Then 0 plus 6 plus 0 is 6. Then next we'll have 0 plus 0 plus 0. Then we'll have 0 plus 0 plus 0. Here we'll have 0 plus 0 plus 4. Here we'll have 2 plus 0 plus 0. Here we'll have 3 minus 3 plus 0. And here we'll have 0 minus 6 and plus 0. And that gives us our matrix. And we go back to what we did before and we obtain the same matrix. So that this confirms our result from before. Okay, but this time we use theorem 2.11.